Hey, you're good at this.
Where's Kenneth?
What's that?
Where's Kenneth?
Is he in school? I don't think he only have one. He should work. It's fine. Oh, you're recording it. That's okay. Right here. Also, yeah, yeah. I saw signs at chapter 4. The parking lot cameras, I remember back years ago, they'd stop after 5. It's 10. They stand out. They use the stand off. So it's all digital. Oh, dang. So if they drive by, they can. When was your first year here? My first year used to really good. Very trouble. It was here before the paint. Yeah, and I lived across the street. So she couldn't believe it to me. Oh, that's again. I wake up trying to pull out my parking lot, parking. Yep. Park home parking. Right there. Sure. Right there. There's trouble parking. I had plenty of things that did that for the houses. The 5:30. Oh, no. Yeah. That's not fair. Three. Oh. Oh. Okay. Through the slides explaining. We like look at what he posted. Yeah. Did you ever Dr. Center? That's why I had it here. Oh, yeah, yeah. Oh, it's talking to me.
It's great. I wrote this note like 2 years ago, and it's still here. It said, please turn off the projector when you're done. I've been taught in this class in 2 years. It's still there. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? All right, good to see everyone. Good to meet everyone. So my name is Professor Justin Tran. So I will be your instructor for EGME 541, finite element method for mechanical engineering. Okay, so today is the first lecture, first of many. And so, today I don't have anything real planned. And so we're just going to go over just a brief overview of the course, we're going to talk about what this course is all about, what to expect. We're going to go over the syllabus and the course website. And so we'll have our first real lecture on Thursday. So today, you can kind of sit back, enjoy it, enjoy the meager jokes I can muster on 3 hours of sleep. Fun fact about me, I had a kid recently and he loves waking up middle of the night. So every day I'm coming in, I'm working on like 3 hours of sleep. So this semester is going to be a great time. Okay. All right. So a little bit about myself. So my office is in E220. So if you don't know, that's in the engineering building. That's the building across the quad, second floor. So you take the elevator up, you turn right, and I'm in the corner on that side. Right. My email address, justran@fullerton.edu. I know it looks like I stole that email address from a running club here at Fullerton, but it's just an unfortunate combination of the letters in my name. So I have my email address there. That's primarily how you will contact me outside of class. Usually I'm pretty quick with email, so definitely be familiar with that email address. I grew up around here. So I grew up in Cypress, California. So if you don't know where that is, that's about 10 miles west here on the 91. So I'm very familiar with this area. I had a bunch of friends that came here to Cal State Fullerton. My educational background has been taking me all over California. So I got my bachelor's from UCLA, my master's from UCSC, my PhD from Stanford, all in mechanical engineering. And my research interests actually does have a bit to do with this class. And so what I do is I do finite element analysis of blood flow inside human bodies to study heart and blood disease. And of course, just being an educator in engineering, I'm also interested in STEM education, better ways that we can do this, more effective ways that we can teach STEM. Okay. All right, next thing I want to go over is the class learning objectives. And so this is something that you will see a lot during the semester. So at the beginning of every lecture, I like to post the learning objectives for the day. And so you can view these in a couple of different ways. And so on the one hand, you can just see them as just a brief outline of the topics that we're going to cover for that day. And so just so that you kind of know what to expect on a given day. But I write these kind of very intentionally. So if you look at every learning objective that I have here, you'll notice that every single one of them starts with the verb. And that's on purpose because, I write my learning objectives from the perspective of, they kind of describe to you what skill that you can learn from the lecture today that you can demonstrate later on. Right? So for instance, the first learning objective that we have here is, describe the use and utility of finite element analysis in engineering work. And so after the class today, you should be able to do that learning objective. And so, if someone stopped you in the hallway and said, hey, describe the use and utility of FEA, you should be able to tell them through today's lecture, okay? And so after every, for most lectures, we'll have things like, perform finite element analysis on a beam, perform finite analysis on a truss, right? So that's kind of how I write these learning objectives. It's not just a summary of the topics, but, a description of the skills that you should learn from each class. Okay. So I always encourage people, I always have these up, before the lecture. I try to come in. I do have a class right before this. So I'll usually come in about 10 minutes before the lecture. This will be the first thing I put up. So I always encourage people to write this down in their notes, just to kind of help organize your notes and to help kind of prepare yourself for each lecture. Today, of course you can write it down, but today is kind of just an introduction day. So not too important for today. Okay. Okay. So what is finite element analysis? And so I'm sure that, a lot of you have probably heard of it, especially if you've taken, 410 here. But in a nutshell, finite element analysis is a numerical technique for solving differential equations on arbitrary geometries. So that may or may not be consistent with what you know of FEA, because, a lot of people associate FEA with the software. So, and so one popular software that is used a lot is called ANSYS. But finite element analysis is more than just ANSYS. It's a description of the underlying theory of the math, of the algorithms, of the equations that kind of go into a program like that. Okay. And so the idea with FEA is that we're going to leverage basically the computational power of our computers to perform calculations at much higher capacities and much higher speeds than you can do by hand. Okay. And so in that sense, FEA is kind of an interesting topic in that, we're not really going to be doing any solving ourselves. But the whole goal with FEA and FEA theory is to properly set up a problem, or to take, a practical problem and set it up in such a way that a computer can solve it from there. Okay. And so by doing so, by performing FEA, it allows engineers to predict how a physical system will react when subjected to external effects. Okay. And so that's kind of where the application comes in for engineering context, where, a lot of times, when you're working as an engineer, you have some kind of engineering system, some kind of engineering product or project, and you want to see or simulate, how your system will react if you apply a certain load to it, if you apply certain constraints to it, if you apply certain heat to it, right? You want to do this without having to actually perform a physical test. Because oftentimes, performing a physical test, making a prototype, setting up the experiments, a lot of times that's very costly in terms of money, but also in terms of time as well. And so FEA has kind of become kind of a core, I would say, part of the design and improvement and analysis process in a lot of engineering firms today. Okay. And so, at the end of the day, the reason we learn FEA as engineers is that, it allows us to design and analyze engineering systems with very complex conditions that we normally otherwise wouldn't be able to do with just hand calculations or experiments. Okay. Okay. And so in general, if you're talking about performing analysis on an engineering system, there are three, I would say, broad categories that you can classify each method as. So one is called analytical. So these are what I call kind of pen and paper calculations. And so these are kind of what you see in a more traditional engineering course, where you learn the theory, you learn the equations, and you solve those equations by hand. Okay. So this is very, this is probably the quickest and easiest or quickest and fastest way to actually perform calculations. But it is very limited. And so, you can't really do pen and paper calculations on anything too complex, whether that be complex geometry or complex loading. You're really limited just because, we can only do so many calculations in our head. Okay? The next type of analysis you can do is called experimental. So experimental analysis is, going out and actually conducting a physical test and collecting data. And so, if you want to get, concrete evidence or concrete, data in terms of how a physical system will perform, there's no better way to do it than running an experiment to do it. Because there's no really questioning the result. Because, if you run an experiment and it happens, there's no questioning it. It actually happens. So there's no, there's no second guessing it. But of course, like I mentioned, the downside to experiments is that it can be very costly and very time consuming to do. Okay. And so the third method, and so this is kind of where we'll be in this class, is to do what's called a computational analysis, where, computational is similar to analytical in the sense that, we're going to be solving governing equations or governing differential equations, but we're not going to be doing it by hand. Instead, we're going to be using computers to do this for us. Which, on the surface kind of seems like it kind of has the best of both worlds, where, we're able to do things very fast and very easily because we're doing things on a computer, and we can handle very complex situations as well. The downside is that computational analysis is, I would say, deceptively very difficult to set up properly, and you can make a lot of mistakes and get results that, sometimes make no sense at all. And so, that's kind of where this class comes in, where, we're going to learn the theory of FEA. We're going to learn how to properly set things up so that you can get reliable results from your computational simulations that you can apply towards your engineering. Okay. Okay. So I want to give you some examples here. So, if you were to do an analysis on a beam, for example, a problem like this would be something that you probably learned in your solid mechanics course. So you have a beam, very simple geometry. It's basically one-dimensional geometry. You have very simple loading. In this case, you have a very even distributed load on top, and you want to solve for the deflection of the beam, right? Very simple boundary conditions. We have a kind of a a pin support on the left-hand side, a roller support on the right-hand side. This is something that we can solve by hand, right? But if you were to do an analysis on something like this, so this might be a structure that you may see, kind of maybe this is kind of the bare bone structure of a parking lot. Parking lot was the first thing I thought of, but this is a massive parking lot. This is like 10 floors of parking, which kind of seems like a nightmare. But if you were to do an analysis on this, where essentially a structure like this is composed of a bunch of beams, right? This is something that you would not be able to really do by hand. And this is something you can't really do experiments for either, because you can't exactly construct a 10-story parking structure in your backyard. So you would need to use simulations to do an analysis of this. Okay. All right. So most of the examples that we're going to do in this class, I think probably the first thing people think of when they think of FEA is do structural analysis. But you can actually do any kind of analysis, as you want in FEA, as long as it's governed by a differential equation. And so another example that's very common is to do thermal analysis or heat transfer, right? So this might be a problem that you see in your heat transfer class. You're looking for the temperature distribution in a square wall, where the temperature varies from T1 on the left to T2 on the right. It's a very simple one-dimensional problem, very simple geometries, very simple conditions. This is something you can solve by hand. But once you start to add some complexity in terms of geometry, here we have a very complex turbine geometry. It looks like we have very complex heating. We might have hot fluid that's kind of striking it. This is something that you would have to do in a computer, and again, would be very expensive to set up, right? Especially if you're doing limit testing. So, one common application for simulations is to do limit testing in terms of, how much heat can our turbine experience, or how much load can our structure experience. That's not really something you want to be doing with experiments, or at least not too much, because, by doing limit testing, you're kind of destroying your prototype, and prototypes are kind of expensive to produce. Right, and so the last example I'll give is fluid flow. So, if you want to analyze flow in a pipe, this is a very simple problem that you can solve by hand. But if you want to add any kind of complexity, and so, this is a little preview of kind of the work that I do. So this is a simulation of blood flow in a patient with what's called a shunt. So this here, it's a little bit hard to see, but there's a connection between these two blood vessels right here. Normally that's not there in a normal person, but this is something that was surgically added for medical reasons for this patient. So we can simulate this in a computer and see how we would perform, before we actually try this out on a real person, which is, obviously has a lot of real benefits to not putting people's lives at risk for experimental procedures like this. Okay. Okay. So that's kind of the idea with FEA. So FEA kind of is the backbone for a lot of these simulation tools that allow you to do very complex and very practical simulations for engineering work. Okay. Any questions on this so far? Good. Okay. So this is a grad class, so I usually skip this, but I'm sure everyone's coming in with their own kind of examples as well. Okay. Okay. So one question I get a lot is, we have several FEA courses available for you to take. And in particular, we have two FEA courses at the graduate level. So we have this class 541, and we have the other class that I teach, I kind of teach one every other year, 540. So 540 is the other FEA class. And so I get asked, what's the difference between these two classes? Well, 540 is kind of more, I kind of call that more the applications course. And so 540 has more of an emphasis on ANSYS. And so we do a lot more hands-on in terms of, using the software, applying it to practical problems, going over some of the advanced features in the software. 541, which is this class, we focus a lot more on the theory. And so, we're going to go over like the equations of FEA, how to develop the equations for that, how to write your own code for FEA. We're going to do a little bit of ANSYS in this class, and so I have a couple ANSYS activities just because, I know as grad students, you guys don't always get to pick kind of what, when you get to take courses, and so for some of you, this is going to be the only FEA course that you take during your time here, and so I want to make sure I cover a little bit of ANSYS, just so you kind of have that in your back pocket to kind of take back to your employer or to take back or to put on your resume. But the emphasis for this class and the goal of this class is to learn theory, okay? And so part of that is to learn, what I call the finite element process is. And so how to take kind of a practical engineering problem and turn it into something that we can solve with FEA, okay? So the first step in the FEA process is to do what I call discretize the geometry. Okay. And so when you have a generic kind of arbitrary geometry, of say like a car or something like that, right? That already is something that's very difficult for a computer to analyze and to solve. And so to make things a little bit easier for the computer, we need to discretize it. In other words, kind of take your geometry and break it up into much simpler shapes. Okay. So you can see here, we have what's called a mesh on this geometry. So this geometry here is not too difficult. It's basically just a connecting pipe. But there is some complexity here. So, this kind of flange here is kind of a complex geometry. You have kind of a square thing here with a fillet and some holes. And so not the easiest thing to do by hand. And so, even something like this, we've broken up to all these little squares. You might see there might be some triangular elements here, right? So this is kind of a necessary step because, ultimately what we're going to do is we're going to be solving some differential equations on this geometry, okay? And we can't do this, or a computer can't do this without breaking it up into simple shapes first, okay? So this step here is often called meshing. So that's kind of the name that you'll hear given to it the most in these situations. But essentially, we're discretizing the geometry, okay? And each individual shape here is called an element, hence the name finite element process or finite element analysis, okay? Okay, and so the next step is to do what I call assume a functional representation. So this step is not going to make that much sense right now. So this step will kind of make a lot more sense kind of once we start diving into the theory. But one thing you have to do in the FEA is to basically assume a form of the solution, right? And so we have this very complex differential equation that we're trying to solve. We're trying to solve it on this very complex geometry. And so to kind of help make things a little bit simpler for us, simpler for the computer, we kind of make an assumption beforehand in terms of what the functional form of the solution looks like. And so oftentimes these are going to be very simple polynomials. So they're going to be linear polynomials, quadratic polynomials. So this kind of helps us generate a solution, okay? And so these functions, which we're going to talk about a lot in this class, are called shape functions, okay? All right, but that's kind of one key step of the finite element process. And one step that's actually quite unique, because a lot of times, when you have an equation that you're solving that you might see in another class, right? A lot of times you don't really make any assumptions in terms of what the solution looks like. You just take the equation and you solve it. But with FEA, we kind of go backwards a little bit, where we say, okay, I have this complex equation. What if the solution looked like this? What if it looked like a linear function? And we try to find the best linear function that solves that equation, right? So that's kind of the key step here for the FEA process. Okay. Next step is to assemble, right? And so one thing that you'll see is that, one hallmark of the FEA process is that we're going to take a very complex engineering problem with complex loading, and we're essentially going to turn it into a linear algebra problem. So a linear set of equations with a linear set of unknowns, okay? And when you have a set of linear equations, the best way to represent that is with a matrix, okay? So this 5 by 5 matrix here represents a set of 5 equations and 5 unknowns, okay? And this step of kind of taking our problem and assembling this matrix system is called assembly, okay? Now this example here, I have this 5 by 5 here just because it's easy to see, but in reality, especially with problems that ANSYS is solving, that your computer can be solving, these linear systems are going to be much, much bigger. How much bigger, you ask? It's not that uncommon to have, matrices that have, 1 million rows and 1 million columns. And that's still fairly modest. And so you may get, I've seen systems that have, hundreds of millions of rows and hundreds of millions of columns. And so that's obviously something that you can't solve by hand. Because I've had classes before where I show this slide and I talk about, we're developing the system, and someone raised their hand, like, oh, I can solve that. That's no problem. I'm like, yeah, you can solve a 5 by 5 system, but try 1 million by 1 million and see how you do with that. So so I have this here just for visualization, but in reality, these linear systems are much, much bigger, okay? Which again, in FEA, we're not really solving these systems. A lot of times, when you're working on theory, this is about as far as you're going to go. And so you'll get as far as, setting up a linear system, and then you're going to let the computer solve it from there. Okay. Next step is to apply boundary conditions. And so this kind of gets you back to the physical problem a little bit. And so every finite element simulation, you need to have boundary conditions. And so boundary conditions represent any kind of external effects that are going to be being applied to your geometry. So any kind of constraints, any kind of loads, forces, heat fluxes, things like that, temperatures, anything that's not being modeled in the CAD geometry that's going to have an effect on your solution, you need to model in the boundary conditions, okay? And so in this class, we're going to be spending quite a bit of time in terms of how do we mathematically represent these boundary conditions and how do they affect our solution, okay? Okay, next step is to solve. And so, this part seems the most intimidating, but this is the easiest part because, this is where we're going to say, all right, computer, take the wheel. You're good. I'm going to go get a coffee or something like that. So, we've done all the hard work. We've set up the equations. We set up our matrix. We've applied our boundary condition, and we look at it. All right, I have a 1 million by 1 million linear system. I ain't solving that. So, we're letting the computer solve it for us. So, and even when we're developing our own code, there's easy ways to get the computer to solve this for us as well. Okay. So this is literally, one line of code, but this is kind of where most of the work happens, right? This is where the computer is going to be solving a linear system. Okay. And then the last step to the FEA process is post-processing. And so oftentimes, when you run an FEA simulation, you get, I would say, very raw results. And so results that aren't maybe not immediately useful for your engineering application. And so there's a little bit of post-processing, a little bit of visualization that you have to do in order to get the result into a form that you can actually use for analysis, that you can actually use to actually produce results, okay? And so we'll talk a little bit about that as well. So we're not going to get too much into that in this class because, again, we're focusing mostly on theory. But, this will be a thing when we do our ANSYS activities. Okay. Any questions so far? Okay, good. Okay. All right. Next thing I want to talk about is, just emphasizing the fact that FEA is just a tool. I think, FEA is kind of romanticized a little bit, especially it's very trendy right now in terms of, people think it's this kind of God tool which can give you the results. But it's not like that, and it's no better of a tool than like a hammer or a screwdriver, right? And so yes, it does enable you to do really cool things as an engineer, but there's also a lot of ways to misuse it, and there's a lot of ways to get results that are not useful to you at all. Okay, and it's not going to do your analysis for you. There's still a lot of work that you need to do to actually properly set it up. Okay. And so there's a very common phrase that you'll hear in FEA, and you'll hear me say this a lot in this class as well, which is garbage in, garbage out. And so, if you do not set up your FEA simulation properly, if you don't set up your boundary conditions properly, your mesh is not good, we call that garbage in. And so that means you're going to get garbage out. And so you're not going to get things that are useful. You're going to get results that don't make any sense, right? And so a lot of the, I guess, a lot of the challenge of using FEA is to make sure that what you're putting into FEA is actually useful so that you get something useful out of it, okay? And, most importantly, what you get from FEA, even when you do set up everything properly, it's important to remember that FEA only gives you approximations of the solution, right? So remember before, when we talked about the FEA process, there's a part where we have to assume a functional form, right? And so, even when you set up everything properly, the results that you get may not be exact, right? That's not to say that, what you get from FEA can't be useful. It's just, just kind of be aware of the limitations and, being aware of that can kind of help you make the most, okay? And so that's something we're going to talk about a lot in this class as well. So, what are the limitations of FEA? What are the nature of these approximations and how close can we actually get to the real thing, and how do we minimize the errors as much as possible, okay? Okay. All right, so let's go through an overview of the class. And so, this class kind of follows a very kind of linear structure, I would say. So we're starting over at the left, and we're going to progress to the right. Okay. So first thing we're going to go over in this class is what I call the direct stiffness method. So this is kind of the first kind of theory that everyone learns in FEA. It's relatively simple, but I think it kind of does a good job of kind of laying out kind of theoretically in terms of what you can do, okay? Or how the FEA process actually works, okay? From there, we'll go on to kind of a bit more modern FEA. So, the direct stiffness method, great for learning, but, there's basically no software out there that's based on the direct stiffness method anymore. So we'll use that as kind of the basis to learn, I would say, more modern theory. So finite element solutions to differential equations, that's the theory that basically all modern softwares are based off of, okay? So that's when the class will kind of really start to pick up. We'll get into these differential equations. We'll get into kind of more complex math, but after doing the direct stiffness method, the idea is that this is a little bit less intimidating. Okay. And then from there, we'll get into for the final couple 2-3 weeks of the class, we'll kind of go over more kind of practical FEA considerations. And so during that time, you'll be working on your final project. We'll be going over kind of miscellaneous topics and things that you should know as kind of a practical FEA practitioner. Okay. Right, and so this is kind of a bigger breakdown of the topics, and so there isn't, and so one thing may have stood out to a lot of you is that there is going to be some MATLAB, right? And so there is going to be some programming that you're going to have to do in this class, because the final project for this class is going to be to write your own FEA code in MATLAB. And so there is going to be some programming involved. And so, we are going to do a review. And so, I'm not going to just toss you guys to the wolves. We are going to do some reviews that, we can kind of brush up on stuff, just because I know it could be a bit of, for some of you, it might have been a bit of time since you've taken MATLAB or since you've used it. So, but it's a good skill to know, especially as we go through this class. Okay. All right. Any questions on this so far? Okay. So one question that you were going to ask a lot in this class, just because, I know a lot of you are kind of just eager to use ANSYS. And so why are we bothering with all this background knowledge? Why are we bothering with the theory, right? Well, the short answer to that is, you can take 540 next year. But, I think with any kind of complex topic with FEA, yes, it's important to know the practical application. It's important to know how to use the software. But if you're going to be doing this professionally, especially with the master's degree, I think you also need to have a strong understanding of the theory, to kind of back up that practical application. Okay. Because the thing is, with FEA, you'll learn very quickly that, when you're doing these kind of very, I would say simple problems or box problems that we're going to do in this class, things seem very simple, right? And so it's like, you're using ANSYS, like click here, set this here. Things turn out really nicely. Real life is never really quite like that. And so, a lot of times, if you're working as an FEA analyst for a company, you're going to be given a problem. And so your boss is going to give you a geometry. It's going to give you a condition, say, hey, we need some data. We need to simulate this, figure it out. You're going to figure out very quickly that, the real problems don't really fit into those very nice, problems that you did in the class. And so you're going to have to adapt and kind of be flexible a little bit and kind of, where you kind of make assumptions, right? And so, there's really no good way to teach all of that, just because there's so many different situations that can arise. And so kind of the best way to kind of, be prepared for that is to really have a strong understanding of the theory behind it. If you have a strong understanding of the theory, then you can kind of handle these situations that wasn't explicitly taught in the class, okay? Because you're also going to run into problems, right? And so, when you try to run simulations, it's going to fail a lot. And so you're going to get errors, not only in your coding, but also in running, the commercial software as well. And so, knowing the theory will help you kind of get through that, okay? Because, when you guys leave this class, I want you guys to have the confidence to say that, I am an expert in FEA analysis. And as an expert, it's your responsibility to really have a deep understanding of your tools and kind of be honest about the limitations of that. And you really can't do that unless you have a strong understanding of the theory and the math behind all these different methods. Okay. So for example, let's talk about another profession. So let's talk about a vet. Okay. So on the one hand, a vet needs to know what I call procedural skills. And so how to give a shot to your cat, how to take a blood sample. How to perform an eye and ear checks, right? And so when you go to the vet, physically, this is kind of what you see a vet doing to your animal, right? And so, a lot of people kind of get lulled into the sense of like, yeah, I can do that. I can give a shot to my animal, right? But what you don't see is that there's a lot of conceptual knowledge that goes behind, being a vet, right? It's not just going through the motions of, giving a shot to an animal, taking a blood sample. You need to know why you're giving your animal a shot, when to give it, where to give it, right? You need to understand why an animal is sick and what to do, right? You need to interpret animal behavior, right? So all of this kind of comes, not from the procedural stuff, but from understanding the theory, understanding the concepts behind doing veterinary work, right? And so it's the same thing for us as engineers. It's not just knowing where to click in ANSYS. It's more than just knowing what buttons to push. You need to have a conceptual understanding behind it, so you know exactly why you're doing certain steps, so that when you do run into issues or complex situations, you know exactly what to do, or at least how to adapt. Okay. Okay. And so once again, for 541, we're going to focus on theory. Okay. We're going to do a little bit of ANSYS, but that's definitely not the focus of this class. And so we're going to be doing equations. We're going to be lots of math and do lots of programming. And so, I want to be kind of honest with you guys up front about that, because, I think the first time I taught this class, I maybe didn't warn people ahead of time. And then they're like, why are we doing in MATLAB? What are we doing this? Why are we doing all these equations? I just wanted to do ANSYS, right? But that's why I kind of want to be straight up with this. Okay. Okay. And so the final project for this class, it's kind of already determined. I've taught this class a few times. You'll be writing your own FEA code to solve a 2D heat transfer problem using finite elements. Okay. It sounds very intimidating, right? But by the time you get there and by the time you finish, I promise you, it's going to be very satisfying to see those color plots and say like, yeah, I wrote the code for that. I solved the equations for that. I wrote this 200 line code to do that, right? It sounds scary, but I promise you, it's there's a reason why the semester is 15 weeks, and so we're not just going to be screwing around for 15 weeks. We're building up the theory, and you'll be doing something really cool by the end. Okay. All right. So I think that's it before the syllabus. Any questions on just kind of the introduction to the class, kind of what to expect before we start talking about the syllabus? Okay. All right. So let's start talking about the syllabus. Okay. So everything, from the syllabus, I posted the syllabus online. I think I emailed it to everyone as well. But just know that you can, so everything we cover here is on there. Okay. So my office, once again, my office is an E220. I know for grad students, it's probably not going to work out all that much, because I usually go home right after this, because I know a lot of you guys just come in the evening. But if you're here during the day, that's where I'll typically be. But I'm also available over Zoom. Okay. So my office hours this semester, I have it on 3 days. So it's going to be Monday, Tuesday, Thursday. Mondays and Tuesdays are going to be from 2:30 to 3:30, and then Thursdays are going to be from 1 to 2. So I know what everyone's thinking right away. I know these times are not ideal for grad students. I usually don't like to have all my office hours bunched up in the same time. I usually like to have one office hours in the evening, especially for grad students, because I know you guys have a lot of you are working or busy during the day. But I have a kid at home, and my wife's actually been crying for help, and so I need to go home right after this. So that's kind of the best I can do. So that. But just know that, I am available outside of this as well. And so, if you want to talk to me about homework, you want to talk to me about the project, or, you want to ask clarification on the lecture notes, but you can't make it to office hours, just send me an email, and we can find a time to chat. And so, I've met with students on the weekends as well. And so, I know with grad students, I know, you guys have kind of crazy schedules. And so, I try to be as accommodating as I can. So just shoot me an email, and we can usually set up a time. But at least those times, I am definitely going to be available. I'll be available physically in my office and also on Zoom as well. Okay. And so we'll go over the course website later, but you'll see that there are going to be Zoom links for all the office hours as well. So you can join via Zoom. Okay. Course learning objectives. And so, like I mentioned at the beginning of class, I use these learning objectives a lot. So lecture by lecture or week by week, we're going to have kind of, I call them kind of fine-grained learning objectives in terms of what we're going to cover that week. But I also have learning objectives in terms of, what we're going to cover on the course in general. Okay. So I have these 5 learning objectives for this course, and I use these learning objectives to kind of organize all of the content for the course, right? And so, I'm not just doing things randomly throughout the class. I have these as kind of organizing principles, right? So everything that we're going to do in this class is going to be in support of these learning objectives, so that by the time we finish the class, you should be able to do all 5 of these learning objectives. Okay. So I won't go over them in detail now, just because I think they'll make more sense as we kind of go through the semester. But just know that these are always kind of in the background for this class. Okay. So let's talk deliverables. So there will be 7 homework assignments, which includes the ANSYS activity. So I think I have 2 ANSYS activities planned, or 3. I think I have 3. So 3 of those homework assignments are going to be ANSYS activities. 4 will just be kind of traditional problem sets. Okay. There will be 2 midterm exams, and so the midterm exams will be in person, so you have to be present for those, and 1 final project. So there's going to be no final exam, so it's just going to be a final project. Okay. The lowest homework will be dropped, just because I know that things get crazy during the semester. So I don't want you guys to feel like you have to do everything on time, just because I know it's hard to kind of stay on top of the deadlines. But please still do them all, right? So I don't give you guys busy work. I know every instructor says that, but I mean it. So I give you homework with a purpose, right? To kind of practice what we cover in the lecture. So even if you can't do it by the deadline, please still do it, because those homework assignments are an important part of this class. They're part of the experience. Okay. And one thing that's not mentioned here, I always forget to put it, but you guys are grad students, you guys are adults. I don't need to police you guys as much. And so all the homework assignments will be graded just based on completion. And so when I'm grading your homework and I'm going through it and I see that you made an honest effort for everything, you don't necessarily have to get the right answer, but as long as I can see that you put a good amount of effort in, then you're going to get full credit for the homework assignments. Okay. The midterm exams will not be cumulative, and so each midterm exam will cover about a 6 or 7 week span of content. I know that was a meme. That wasn't intentional. That's just how it came out. And so, the midterm exam, you won't just have to account for just a small chunk, but the final project will be cumulative in a sense, in that it will require knowledge that's been gained throughout the entire course. Okay. All right. And so the last bullet point there is all the dates that I have for everything. So the 2 midterms, the first midterm is planned for Tuesday, March 10th. The second midterm is planned for Thursday, April 23rd. And the final report or final project is due the Sunday after finals week. So that's Sunday, May 17th by 11:59 p.m. Okay. So the 2 midterm dates are flexible. And so, usually for grad students, it's usually not an issue, just because you guys aren't taking 4 or 5 classes like my undergrads. But I know things can kind of stack a lot. And so if you have multiple classes with multiple exams, during those weeks, I am open to pushing them back. Those aren't set in stone. So definitely just come talk to me, and we can push those back. Final project, we may have a little bit of flexibility. It kind of depends on how far I am with grading for my undergrad classes. But grades are due the week after that 17th, and so I usually want to give myself enough time to grade. So there may be a little bit of flexibility there, but that's about as far back as I can push it for now. Okay, so let's talk about the grade breakdown. So letter grades we'll start from the bottom and go up. So letter grades are assigned based on your overall class points. So I think this is a fairly standard breakdown. So A's are basically 90% and above, B's are 80% above, C's and D's, so on and so forth. Okay. And in terms of how everything's broken down, so homework is worth 10%. Your 2 midterm exams collectively are worth 60%. I'll explain the higher and lower in just a second. And the final project is worth 30%. Okay. Now, your 2 midterm exams, one of them I'm going to count for 35% of your grade. The other exam I'm going to count for 25%. Okay. And so the way I'm going to determine which to count for 35 and which to count for 25, it's going to depend on your performance on the exam. So whichever of the 2 exams that you score higher, I'm going to count that for a higher percentage of your grade. Okay. So let's say on the first exam, you get 48 out of 50. Second exam, you get 23 out of 50. That 48 out of 50, that's going to be worth 35%. Second exam is going to be worth 25%. Okay. So I do that, to kind of give you a little bit of flexibility, just because I know, an exam is kind of a very interesting thing. It's a very a lot of it kind of has to do with kind of how you're feeling that day, and so a lot of time you'll prepare for an exam, you'll take it, and you don't really do as well as you want to, and so I want to give you guys a sense that you can still kind of make it up. Okay. So if you don't do well in the first exam, you can kind of really make it up and then some on the second exam. That's kind of the way. That's kind of the reason I kind of have it like that. Okay. And then last thing I'll say is that I don't do grade curving, at least not in the traditional sense. So when I was in college, a lot of times the professor would kind of decide even before the semester begins that I'm only going to give A's to 10% of the class, B's to 30%. So I don't do that. But I do grade adjustment or grade scaling. And so what that means is that, once all the final grades are in for everything, so all the exams, the projects, the homeworks, and I see that the overall class average is below what I think it should be for the class. And so for a grad class like this, I'd like the average to be about a B minus. And so I try to aim for 80, 81%. And so let's say after all the grades are in, the overall class average is 75%. And so what I'll then do is I'll go in and I'll add 6 points to everyone's grade to kind of bump the class average up to 80, 81, 80%. And then I'll do that before assigning final grades. And so that's only just there to help. Okay. I know what everyone's thinking. I don't subtract points. And so if everyone does really well in the class, I don't subtract 3 points from everyone's grade. So if everyone does well, there's like an 84, 85%. Great. I kind of just leave it like that. But I only add points to it. Okay, so I'm not a sicko. I don't subtract points from people's grades. All right, textbooks. Let me stop here actually. So any questions on just the deliverables or course grades so far? Okay. Good. All right, textbooks. So textbooks are not required. I'm going to be using two primarily throughout this course. So the first book, the Logan book, literally called the first course in the finite element method. That's the textbook we're going to use primarily for the direct stiffness method. And the other textbook, which is going to be the main one for kind of the modern FEA, is by Kotromanos, Fundamentals of FEA Analysis, Linear Finite Element Analysis. I'm using a 2017 version. I think there was a new version that just came out recently. But as I always tell students is, find a cheap one. It's not required for a reason. And so I post all my lecture notes online. These slides will be online. I post the lecture recordings online. Homework assignments, I'm going to give you the full problem statement, so you don't need to look up problems in the textbook. So, the textbooks are only there if you want to have more detailed, explanations of the theory. You want to see more examples. And so the textbooks are great for that because there's only so much I can cover in the lectures. And my lecture notes, I like to think that they're comprehensive, but they're kind of designed more for me to deliver the content. They're not really meant to be a textbook. And so, there's details I'm going to skip, there's things I'm going to gloss over. And so a lot of those things are in the textbook. So if you do want to reference, these are two really good ones. So I do recommend picking them up, but it's not strictly required. Okay. And if you do really want these textbooks, I always say that, you can pay for a physical one. If you want to have something to display in your office or something like that, that's usually what it's good for. But if you're going to be just getting a PDF of the textbook, don't pay money for PDF. You might be, able to do a little Jack Sparrow on the open web and find a text and find the PDF of the textbook. That's usually what I recommend for that. Don't spend money on an access code or PDF. That's a good one. So, if you're going to get a PDF anyway, then find a sail the high seas. Don't buy from publishers. All right, course website. So we'll be going over this in more detail in a second, but I just want to mention it here. Basically, any content that I produce for the class is going to be posted on Canvas. So lecture notes, lecture slides, homework assignments, homework solutions, exam solutions, study guides, all the tutorials and answers are going to be posted on Canvas. And so I don't hide anything from you guys. So everything I create, I share with you guys, and it's all going to be on Canvas. Okay. So I always recommend students that check the Canvas site regularly. It is going to be updated, at least on a weekly basis, if not more often. So check it for any kind of content. Okay. I also will be making announcements on Canvas. I think Canvas automatically emails that to you. I think everyone I don't think there's anyone on the wait list, so everyone should be getting my emails from Canvas if you're enrolled in the class. But if you want to check the announcements, they're also there on Canvas as well. All right, course policies. And so this is kind of the miscellaneous stuff that didn't really fit into any other categories. Late homeworks, I do accept. And so you can turn in homework after the due date. But I do take points off. And so for every day that the homework is late, after the original due date, I dock 10% off the maximum allowable points. Okay. And if for some reason that you cannot turn it in, and so you can't submit the PDF on Canvas, I know it happens sometimes. Canvas is a weird thing. You can always send your scans to me as well. Okay. Or if you want to, you can physically turn your homeworks in the classroom as well. I know not many people do that now, but you can do that as well. Okay. Regrades, and so I am not a perfect grader, so I do make mistakes in grading, and so if you want to regrade on something, I'm always open to that. If anything, if you just want to discuss, you want to kind of ask questions about why I took points off a certain place on an exam or homework, I'm always open to discuss that, so don't be afraid to ask questions about that. Okay. The only requirement that I have for regrades is that they must be done within a week after I return or grade something and give it back to you. Okay. The reason I have this deadline is, on the one hand, it kind of prevents, the thing that kind of always happens every semester. We get to the end and it's like, oh, I need, 0.3 more points to get an A-. Can you regrade my homework 1? I was like, no, man, that happened like 3 months ago. I'm not going to look back at homework 1 again. But the other thing is that, when I grade your guys' material, maybe not so much for the homeworks, just because it's on completion, but for the projects and for the exams, I'm going to leave you guys comments and feedback. Okay. And I want you guys to read those comments on a timely basis, okay? Because the thing with, feedback and pedagogy and learning theory is that, when you receive feedback like that, comments, they're really only useful to you in that moment, right? It doesn't really do good for you to look back on your 4th grade English papers and seeing what your teacher wrote, because, you're way past that, right? And the same thing kind of goes here as well. So, comments and feedback are really most useful when you're when you just learned that material, okay? And I want you guys to be reading those comments within a timely manner. And so to kind of help encourage that, that's why I kind of place this week limitation on the regrades to make sure that, when I do grade something, I give it back to you. I want you guys to be reading that feedback right away and not just looking at the number and just closing it and just tossing it into the garbage, okay? Okay, so last thing on this page here is the emails. And so if you're going to be emailing me about this class, please include EGME 541 in the subject line. So I get a lot of emails, and so I'm teaching 2 other classes, 2 other undergraduate classes. And so undergrads send me a lot of emails. And so, kind of helps me out to kind of sort through my inbox if you include EGME 541 in the subject line, okay? Because typically the way that I answer emails is that usually I wake up in the morning, I go to my computer and I have, 15, 20 emails I need to respond to. Usually I'll do them in chunks. And so I say, let me answer my grad students first. Let me answer all the 541 emails. Then let me answer all my 308 emails, then my 436 emails. And so if you can kind of help me sort my inbox by including the sub 541 in the subject line, that just kind of helps me out. And if you do so, then I promise I will get back to you in a timely manner. So usually I'm pretty quick with email, so usually I'll get back to you, usually same day, usually within 5 minutes if I just happen to be on the computer. But at most, 48 hours, I'll get back to you, in email, not including weekends, of course. Weekends are for spending time with my son. Okay, so last thing I want to discuss before we get to the course website is academic dishonesty. So, it's not a comfortable conversation we have to have, and I know you guys are grad students, you guys are all adults here. It's kind of more for my undergrads, but we have very strict policies on academic dishonesty here in the college, here at the university. Basically, it will not be tolerated. Okay. So basically, any way that you're going to, any method that you can use to get something else to do the work for you, whether that be copying the work off your friend, or getting the answer on Chegg, although I think Chegg's going out of business now because of ChatGPT, or the most popular way to do things nowadays is to ask ChatGPT or some other AI tool to do your work for you. All of that, none of that is going to be allowed. Okay. And I have a pretty hardline stance on this. I know it's kind of a hot topic in higher ed right now. Is what are we going to do with AI? I have a very hardline stance, but I think also a very simple stance, where it's just not going to be tolerated. Okay. And I want to kind of justify that a little bit, just because I think there's a conversation to be had, because I think the reason you guys are taking this class is not just to do the work and to get a grade at the end, right? You're taking a course like this to gain skills that you're going to use in the workplace, right? Now, I'm aware that a lot of engineering work now, a lot of times, you guys are going to exit this class, you're going to graduate, and you're going to be relying heavily on AI tools for your work, right? I think that's inevitable. I think that's going to be the world that we're going to live in, right? But it's one thing to to work for a company and to have your boss ask you to do something, right? And if that's something that just needs to be done, that's going to be sold to make the CEO of your company just a rich man, then yeah, who gives a shit? Just use AI to do that. You're not meant to get anything from that experience other than just to get paid for it. But a classroom is different, right? So in a classroom, you're taking this class to actually learn something, right? And end of the day is that if you're using AI to do your work for you, or even to help you, help you with the hard parts of the work, you're not getting what you need to out of this class. You're not gaining the skills, right? You're just proving that the AI can do this work, which I know that this class is AI can do a lot of the work in this class. I'll be honest, right? We're not going to be doing really complicated engineering stuff, right? An AI tool may not be able to get you an A, but it might be able to get you maybe like 6 or 7 out of 10, on those types of assignments. Okay. But that's not the point of taking a class like this. A point of taking a class like this is to learn skills, right? And even if you are going to be using AI to help you with your FEA outside of this, right? You need to be able to determine or to assess whether what you get from an AI is actually reliable, right? Because I think that's going to be a really important skill in the future. And I'm of the belief that you can't really do that unless you have a firm understanding of the skills of the theory, going into that, right? So that's why I take a hard stance against AI. I know it's going to be tempting, especially for the final report. I know, it makes your report writing easy, but believe it or not, it's very easy for me to determine whether a report is written by AI or written by a person. Just because, I don't think AI is on the level where they can write a finite element report and talk about the results in detail like a human being. Okay. All right. And so, kind of the compromise I have for this is that, my job here as an instructor, as what CalState Fullerton pays me to do, is to help you guys succeed, right? I've done it before where, I failed students for using AI. I failed students for using a phone during an exam, but, it's not fun for me. And so I'm not, and I'm not a sicko. So I'm not a normal person. I get more joy. I get more feelings of satisfaction when when you actually, learn something, you come back and say, hey, that stuff we learned in 541, I'm using that in my job right now. That's what I want. That's what I most want to see. And so I promise you that, I'm going to do everything I can to make sure that you get the skills that you need, you guys get the learning and the skills that you need to succeed, not only in this class, but also in your careers as well. Okay. And so if you ever feel like that you're struggling in the class, you ever feel like that you need to rely on something to kind of get the work done or to do well in an exam, please, I would just ask that you please come talk to me first. And, we'll see what we can do to kind of get you back on track. Okay. So my job here is not to judge you. It's not to look down on you, right? It's not to say, it's not for me to kind of, it's not for me to be a gatekeeper, right? So my job here is to kind of help you guys learn and get the skills that you need. So the only thing I ask is that you give me a chance to do that first, before you turn to some other tool to do it. Okay. Okay. One more slide. I always forget I have this one. So last thing I'll note here is your first homework assignment. So the first homework assignment, there's no calculations involved. I just want you guys to send me an email. And so, so I know I recognize quite a lot of you. So, a lot of you I've met before. You guys have taken my classes before, but, a lot of you are meeting for the first time too. So, first homework is just to send me an email. Just introduce yourself. Just give me your name, your year, your major. And just tell me a little bit about yourself, right? So even if we've met before, even if you've taken my classes before, you're not the same person now that you were, last year or even last month. And so just kind of give me an update on your life, right? And so, I want to, have that relationship because, we'll be stuck together for the next 16 weeks. And so, we might as well know a little bit about each other, right? So you guys know a little bit about me already. I have a son. You know that he keeps me up all night. I'm kind of running on fumes right now. I know I'm just kind of rambling a little bit, but I want to learn about you guys too. Okay. So I have 4 questions here. Feel free to answer these questions, but these questions are not a requirement. The only reason I have these questions is, a lot of times when someone asks me to introduce myself to someone, it's hard for me to kind of know where to start. And so I have these it's just kind of a conversation starter. But don't think of it as like a questionnaire where you have to answer every question. A lot of times I get those emails where it's like, question 1, what kind of career would you like to have after graduating? The kind of career I'd like to have after graduating is this. And so, don't feel like you have to answer these. These are just conversation starters. So, feel free to talk about whatever you want. Or not. You can just say that, I have no interest in getting to know you. Give me credit for this assignment. I'm like, all right, cool. And I'll give you credit for the assignment. Okay. So the due date for this is going to be this Sunday, January 25th. And so if you send me an email before then, you'll get full credit. I read and respond to every single one of these. And so this is not something where I just kind of, just check a box. I do read every single one. You will get a personalized response from me. And I will try to kind of reference as much as I can from your email. I promise you, I'm not putting these through ChatGPT and writing a response that way. I'm the one typing the response. Okay. And so, please do that before Sunday. Okay. And also don't forget to include 541 in the subject. Okay. All right. Any final questions on this before we take a quick tour of the Canvas site? Okay. All right. So let's take a tour of the Canvas site before we wrap up for today. Okay. Okay. So when you go to Canvas, I've turned on student view. So this is what you should see. Okay. So this homepage I know probably looks a little bit different from some other Canvas sites that you've seen. So I've kind of created this custom just because I think this is kind of what it should be. So there's some information about me, my email address, class times, class locations. All of you guys know this, of course, because you are here or you're here on Zoom. Okay. Course description, course learning objectives. These are all just straight from the syllabus. Speaking of syllabus, you can download the syllabus here if you want. Okay. All the Zoom links are here as well. I don't remember if I mentioned this, but you are free to attend the lectures on Zoom, so you don't have to physically be here for the lectures. Just because I know you guys are grad students, I think it helps with a little bit of flexibility. The only days where I require you to be in person in class are going to be on the exam days. So the exams, you cannot take it virtually, but every other day you can attend virtually through Zoom. Okay. And here are all the links and times for the office hours as well, for if you want to attend it virtually. Okay. Okay, so the last thing on the homepage is this thing at the bottom here called the course outline. So you can see I've broken down this semester week by week. Okay. And what you'll notice is that as we go through the semester, these links will become clickable. Okay. So the only one that you can click right now is week 1, just because we're in week 1. So let me kind of show you what a typical weekly page will look like. Okay. So on each weekly page, I have kind of a breakdown a little bit in terms of what we're going to learn that week. So you'll see all the learning objectives for the week. I write a little bit of blurb in terms of what to expect for that week. All the lecture recordings are here. So, I do record all of my lectures on Zoom. So the link to those will be here as well. Usually I upload the lecture recording the next day. Okay. Any homework assignments that are going to be due or any homework assignments that are posted will be here as well. And any kind of files that you need for the week will be here as well. So any kind of lecture notes, homework solutions, handouts, tutorials, study guides will be posted here as well. So usually I get the weekly page up on the Friday before. And so, if you want to check, you want to get a little bit of a preview in terms of what's going to come up the next week, I recommend checking the weekly page on the Friday before. You can download all the lecture notes that you need. But this is definitely a page. These weekly pages are, probably what you're going to frequent the most, especially, just because these have the lecture recordings and all the notes for the week. Okay. All right. Any questions on this so far? Okay. All right, next tab I'm going to look at, I'm going to skip over announcements just because that's pretty straightforward. Next tab here are the assignments. And so all the homework assignments will be posted here. So you can check this page for that. Okay. One thing I want you to be aware of is there's a difference between these 2 dates, right? So every assignment will have 2 dates. One date is going to be the availability date, and the other date is the due date. So the due date is actually when it's due, okay? So this is the date you need to turn in your assignment by if you want to get full credit, okay? Usually I set the availability date to be a week after the due date, and that's only just to give you guys the ability to turn in homeworks late, okay? So don't think that this is the due date. This is not the due date, right? That is the absolute last day to turn it in to get some late credit. But if you want to get full credit, you do need to turn in by this date right here, okay? Okay. Next tab here is grades. And so this is very straightforward. So you can see the breakdown of the grades here. So homework's 10%, midterm exams 35, 25, and the final project 30. And so you can see how the grades are broken down here. I think this will give you your total. So I do grade things. I'm learning more and more instructors don't grade things until the end, which is madness to me. I don't know why you would subject yourself to that torture of grading a whole semester's worth of stuff in a week. That sounds terrible. So I grade things throughout the semester. So you should have a pretty good idea in terms of what your position is, what your grade is, at any given point in the semester. Okay. All right, next tab is people. So these are everyone that's enrolled in the class. So your name should be here. Okay. Next tab is files. And so, if you want to look for a specific file, so you want to look for maybe certain MATLAB code or certain lecture notes or certain assignment, you can find it here. Now I do post all the files within the weekly pages. And so, if you're going week by week and downloading everything from the weekly pages, you'll find everything there. So there's nothing that's in here that's not going to be in the weekly pages, but if you're looking for a very specific file, so you're looking for a specific lecture note, you don't remember what week it's in, you can find that through this page here, okay? And then last tab here is SOQ. So this one, obviously is not activated yet. You can't leave me a one-star review just yet. You have to wait till after the course. So I think this will be available at the end. Okay. All right, and so that's it. So I try to keep the Canvas site clean. So I try not to. I know there's a bunch of weird apps and stuff here that the university pays money for whatever reason, but I try to keep it as clean and organized as possible. Okay. Any final questions before we wrap it up for today? Okay, all right, so that's all I had planned for today. So I will stick around for the next 15 minutes if you have questions for me. But if not, it was great meeting you all. Thank you guys for coming today, and I will see you all on Thursday. Hey, see you again. Good to see you. How's everything?
It's going good. How you doing?
Good. Okay, so.
Heard, yeah.
Yeah.
No, yeah, I might send you a more formal email later on. I will be doing a graduate project with Professor Banks on capitation.
Awesome.
And I wanted to get some, poke your brain more so about how that could be influenced or what considerations you might make since you do like academic as well.
Yeah. No, there's a lot of applications, especially if you're talking injectables. Yeah, there's stuff for that too.
Yeah, because I'm more so interested in like how capitation affects specific geometry and what the damage or what effects are on that.
Okay.
And I know the body has a lot of organic shapes. So
Yeah.
To provide some interesting insight on what I could narrow down my shape profiles.
Yeah. Oh, that sounds good. I know Dr. Banks.
Yeah.
But yeah, I haven't seen yeah, that's
Okay. Yeah. Just wanted to let you know before I bug you with that.
Okay, sounds good.
Alrighty.
All right, see ya.
Hey, I wanted to ask you, so I took a competition of guitars with you like quite a while ago.
Yeah.
And I remember we had to do a final project. Is it going to be similar?
Similar style. The technique is very different.
Okay.
But yeah, that one I developed this class actually almost at the same time I developed that class.
Oh, okay.
Yeah. So it's similar vibe. But this one's a bit more complex.
Yeah.
FEA is a bit more complicated than finite volumes.
Do you think it would be worth it all to look over my the competition notes to then go over this?
Oh yeah. I write the codes in the same style.
Oh, okay.
So yeah, definitely be worth it to go over that. So, if anything, just to brush up on your general MATLAB skills.
Yeah. All right. Thank you.
Yeah.
Oh, sorry. When I saw your work, I sent it, but without the thing about it.
That's fine. I mean, your name's in the center, so yeah, no problem. So sometimes people send it from their personal, as long as you send it from your house, which I think everyone has so far. Then it has your name.
Does it have to be in or what is that practice?
It doesn't have to be. As long as it's 541, because what I do, I literally search in the search bar 541, and then everything comes up, and I just answer everything like that. Yeah.
It's also, it's been a long time since I've done that lab, so I don't know where I stand.
I think it's been a while for a lot of people. We're gonna go fairly quickly, but we are gonna start from the basics and then go from there.
So it's more like the project is gonna be more that lab centric.
It's primarily.
Okay.
You'll see. Yeah.
I was in it. I was trying to get it down 410.
Okay.
I haven't taken 410. If I skip, I'm a grad student. Could I skip it or?
You could, yes.
Okay.
So I know. Yeah. So the thing with this university is that with the grad students, sometimes people coming in and just taking the classes.
Yeah.
So I teach this class, assuming that you have no prior FBA.
Oh, okay.
Yeah. So we are going to go fairly quick over some of the 410 stuff, but I do go over everything.
Okay.
So during that time, I would say that if you feel like it's going too fast, just find out. I can probably give you some additional resources.
Okay. And then I don't know if you know, I'm not waitlisted this class, but how would I get, like, if a professor said they'd add me, like, how would I get the department to add me that class?
So the instructor would have to do that. So the instructor would have to reach out to the department and say, like, I want to add these people from the top 3 people from the wait list, and the department does it from there. So
Okay.
so there's nothing you can do. The instructor has to reach out. To
Okay. All right, thank you.
Yeah, you too. Hi. Oh, great.
I have reached you regarding the thesis option. So I'm doing thesis with doctoral economic evaluation. So I just need a little bit of your help to see if the
Sure.
masters working on getting the thing is like you guys have access to the economic evaluation and all that.
Yeah.
But me and the doctors, we guys are working that we're gonna develop a numerical model of the whole calculation bubble of the
Okay.
So I just need a bit of your help.
Sure. Cavitation is quite complicated to do in FEA. I have to kind of look a bit more and kind of see, just because you have kind of rapid change and property rapid change. It is, yeah. It is quite. It would be quite. I mean, I think you can do it. It's just quite challenging.
Yeah, I'm fine. There is a rough model which you want to have like but we are going to develop. Results from the
He's at UCI.
I think you remember me. I tried to contact with that numerical analysis of a coronary artery. Right?
Oh yeah.
Like in fall or something.
Okay.
So that's how I started thesis with him.
Okay.
In the meanwhile, I'm not like PhD expert student, so I'll be graduating in fall 26.
Okay.
I'm looking for a PhD.
Okay. Awesome.
I just need you. My field is perfectly aligned with you.
Okay. Yeah.
CFP guy, what to say?
Sure. Yeah. No, I think. I think. Yeah. There's a lot of interest in that for sure. I think probably we should have more conversations in the future.
Yeah, that's my target is like we have no PhD here. Like my target is like UC or like
Okay.
Some I got it in California.
Okay. Yeah. No, I think there's always any
I
interest.
have like 5 research papers that
Oh, wow.
published in the domain CFP.
That's great. Oh, that's awesome.
I know how to write the paper, how to pursue the innovation, how to pick the reviews and everything.
Oh, that's great. Yeah, I think you have publications already. I think you're very strong candidates for PhD for sure.
I need to get your help regarding that.
Sure. Yeah. Let's talk more in the future. Yeah. For the next class?
I'm Kevin.
Oh, hi. Justin.
Nice to meet you.
Nice to meet you.
I was actually in your class, the Finite Elements class.
Oh, last year?
Just now. No, just now.
Oh, okay. Oh, you just went to the bathroom, came back.
Yeah.
I see. Yeah, it's always good to stack the classes one after the other.
Yeah.